start streaming. We're going to see if this works by going to my YouTube channel. Let's find out. It's live now, it says. That might be good. And, okay, there is a chat feature. So anybody who is watching this or seeing it online, you can type here, and I will hopefully see it. There. Okay. We'll see if that works. So, good morning. How's everybody doing? How about this ice today, huh? It's not one thing, it's another. Okay. What we're going to do, actually, I don't want to put that one down. I'll keep that one up. So a couple things I wanted to talk about to get started. The first thing being, last time we had a question about what to do if you took notes in your folder, your repository folder, if you went and cloned it, how do you fix it? And I still haven't got a great explanation for you. There's a way of, you have to create your own branch and you have to then update with the master branch to do that. But I haven't made anything to show you how to do that. So if you're going with the cloning the repo idea, which is what what I talked about last time, you may have to clone into a different directory today so it doesn't overwrite what you've done with your text before. I will have a better description for it for you next time. Does that make sense? Okay. So I'm going to just grab my... Oh, look. People are laughing. That's good. Laughing is good. I'll take that. Let's see here. So last time we left off talking about all sorts of fun stuff. Remember? How could you forget? I mean, it was just like one of the best lectures that day. Probably one of the best lectures I gave that day. But the idea that we started off, or where we left off with, was, can you see this okay? Is this visible? Yeah, good. Was that we have, we were getting into what Bayes is. We started talking about posterior distributions. We showed an example with binomial data, or Bernoulli data, really. You had a series of like events that were either positive or negative, and then we had 7 out of 10, and we started showing the analyses, or we started showing what the posterior distribution looks like with different shapes of priors. And that's where we left off. So today I think we're going to start off by taking lecture number 5, which is actually doing that, but doing it in Jagz. So Jagz, to make this lecture work, you're going to have Jagz installed on your computer, and if it isn't installed, you'll have to just come back to the example because it may take a little bit to install it. So Jagz is a program called Just Another Gibbs Sampler. How many of you have used Jagz? All right, there we go. Jagz, you'll note the textbook that we're using refers to WinBugs for code, and Jagz is really kind of based off of bugs. If you read the Jagz manual, it says not wholly unlike bugs, I think it said. So basically, it was, you know, the same. I understand that the bugs project is no longer really being maintained anymore, and so Jagz is sort of kind of taken where bugs left off. It's one of many different Bayes packages out there, but it's kind of all-purpose. The nice thing about Jagz is that it will. So again, you can download Jagz from this link right here on SourceForge, right there. And then what you'll be able to do is install the package. Once it's installed, there are a couple R packages that work really well with it. One is called rjagz, which is the one that's been built by Martin Plummer, I think. He's the one who created Jagz. Then there's R2Jagz, which is a little bit more all-purpose than rjagz. It has some additional features. And honestly, I'm not a super user of either of them. And in working with the lecture this week, I sort of started to wonder if I should really be using R2Jagz, because there's a key part of Jagz that happens in the beginning called adaptation. And I don't know if it's turning that adaptation part off. And so I need to figure that out. I couldn't understand. I couldn't decide from the help manual. By the way, R, we have to put quotes around help, right? It's help. Some people make really good help pages, but it's help. I remember being in grad school when in the early days of R, like 2001, and it was like it was really help. Right? Don't even bother looking. Then there's a package named Coda that shows up. Coda is Convergence Output Diagnostics. I think it's what it stands for. I'm blanking on the name of it. But Coda is a long-standing package. It goes back, was using it back in, I want to say 2005, 2004. It's been around for a long time using for Bayes. And it helps analyze the data once they come back from the Markov chain. Now, if you just install R2 Jagz, it actually depends on the other packages. So it'll install them as well, but I just explicitly put it in here just to start talking about what those packages specifically are, because sometimes you'll want to pick and choose, not just use R2 Jagz the whole time. Any questions? I'll remember to flip over to YouTube when I see that. Okay. So what we're going to do with Coda, what we're going to do is go back, actually with Jagz, is to go back to our example. Our binomial example. And in notation-wise, the notation for this was that capital J is the number of trials. You can think of it as like a coin flip. Little y is the number of successes. So there were 10 trials and 7 successes. And if you recall from last time, that distribution is binomial, and we paired that with a beta distribution for a prior for the probability of a success, right? Which is called theta in the example. So that beta distribution paired with a binomial distribution results in having a posterior distribution that is a beta. So this is one of those nice prior distributions that's called a conjugate prior, where the conjugate prior is a prior in which the family of the distribution of the prior matches the family and the distribution of the posterior. And so it makes for really easy textbook examples getting us started. But later on, you're going to find that there's a lot of motivation to use conjugate priors in general, and those, to me, those are all about efficiency. They enable certain types of algorithms to be used that don't require rejection sampling. So basically, trial and error, trying to guess what a new value should be. So they're much more efficient. Everything is taken in the chain. Yeah.
So conjugated family prior is strong prior.
Not necessarily, and that's a very good point. Very good question to ask. The conjugate is just telling you that the shape or the family of the prior, the distribution of the prior, matches the distribution of the posterior. So in this case, prior is beta, posterior is beta. However, you can specify terms in the prior, in the distribution of the prior, to make it uninformative, right? Very uninformative. So for instance, let me get back to the plot. This is the previous lecture. I think I had a plot in here. Yeah, run all. There it is. Okay, so what you can show with the prior here, this is an example for the prior itself. This is with the beta distribution relies on 2 parameters. I'm calling them alpha and beta, but they go by different names depending on who you are. If you switch those to an alpha of 1 and the beta of 1, the prior is actually a uniform distribution across the space of where that probability is. So that means conjugate priors can be very, very uninformative. They're just very flexible, They're very nice mathematically, because with the conjugate prior, what we were able to see is the posterior distribution for the parameter theta was a beta distribution. So instead of having to do lots of other calculation, once we observed y and j, we could go and figure out the distribution of the posterior distribution of the parameter without doing any other type of computation, any other type of MCMC to go and get it. So it enabled us to quickly get that distribution. Once we have that distribution, then the question becomes, how do we summarize it? Right, which is where we were at the bottom. Good question. Other questions or thoughts? Am I remembering correctly where we left off last time? Whew, good. I once had a professor in grad school who shall go nameless, but I was in a class going with, we were learning multidimensional scaling, which, you know, doesn't show up a whole lot. And this guy gave a lecture one week, and then the next week I actually skipped class. I was involved. There was something going on, and I missed it. I was not just blowing it off, though. And then I heard from my friends in class that he took the exact same lecture and spent 3 hours on it, the next week. And I'm scared to death of being that guy, because I could totally see that happening. Back in grad school, I was like, well, how can you have that happen? Totally see how that happens now. Oh, anyway. So let's talk about Jagz a little bit. Jagz works. Jagz is a standalone program. Okay, so R is its own kind of beautiful thing, and you can download packages, and sometimes they'll compile things, and that. But most of it is linked to R directly. Jagz you can run without R at all. You can just run it from the command line. But that being said, I've never run a Jagz program from the command line, and even in the Jagz manual, it says pretty much, yeah, this is pretty much built to work with R. So you end up using R a lot. So in that regard, the way that R functions is you end up writing your Jagz code as a text in R or as a text object, a character object. In this case, model 01 text has an open quote and then a closed quote at the end. This is like Lavon syntax in R, if you've seen that before. Or if you ever use R to do M+, with the M+ automation package, you have to enclose your syntax for M+ in quotes as well. This, for Jagz, works the same way. Basically, the model syntax works pretty straightforward. It always has to have a model and a brace to open and close it. That's it. If you're writing it as in quotes. So this is the way that the R-Jagz package passes R syntax to Jagz. Sorry, the Jagz syntax built in R to the Jagz program. So here, let's just imagine we're going to run this analysis where, we're going to forget that we're using a conjugate prior, and we can go and get a nice posterior distribution directly from our data, pretty much. And we're going to go and say, well, let's just sample it with MCMC to kind of get a sense for how MCMC works. So here, you'll see we have to specify J being the data for our example here are Y and J here, Y being 7, J being 10. And then alpha and beta are what we call the parameters of the prior. And we often call those hyperparameters, which is sort of a weird term, because if the prior has another thing that's a prior, then those things will be hyperparameters. So it's orders away from data, basically. So we specify all those terms, and we're going to have to find a way to pass that to R as well. I'm going to show that in just a moment. So we have our data. The R syntax up here shows up within the model statement. Anything, just like in R, any line that starts with a pound symbol or a hashtag, whatever you want to call that, right here is a comment. So this is sort of just ways of breaking off our code. And the way that it gets built is that we have to specify sort of backwards here. I always like to start thinking about what's my variable I'm modeling, right? So in our case, what's the likelihood of the data? Now that's the model. That's where all the information is. So Y is effectively that, right? That's our likelihood of the data. And if you remember that, back in our other example here, we said the likelihood function, let me see if I can find it here real quick. It's effectively, I've lost Y, but in my notation I'm already saying bad things, so not good either. But I've lost it now. Okay, well, this is the posterior distribution. The posterior distribution involves likelihood of the data. It's actually right here. Let's see if I can bring this up. Right here. There we go. This is what we have. The posterior distribution, which is theta, which is our probability, Y, which is the number of times a success happened, and J, which is the number of trials, is proportional to the likelihood of the data times the likelihood of the prior. And so at the end of last time, we had this little mapping of where things showed up. This may or may not be helpful to you. Personally, for me, it doesn't help at all. I just like to think of the formula itself. And so what we need to specify, what I like to specify first, is the likelihood of the data. So what is the likelihood of the data? In our example, likelihood of the data is a binomial variable. And so in Jagz, you take the variable name that you're going to pass to it, right? So this is called y. So we have to pass it something called y. And we're going to say that y, whenever in Jagz you see the tilde character, that's distributed. That is saying this variable is going to have a distribution. Right? It's sort of agnostic as to whether that's a prior or whether that's a data distribution. It depends on what's on the left-hand side of the tilde. But once we pass it y, it will know that's a likelihood function. That's actually data that goes into that. So we're going to say that y follows a dbin. Okay, so that's the next step. In Jagz, the Jagz user manual, which I have a link to in the file, but I'll just pull up here. The Jagz user manual is a good thing to pull up because it will have a set of distributions in it. And so if you want to understand what are those distributions, you can find it there. They're not entirely mapped on to R because in R, the binomial is dbinom, whereas in Jagz, it's dbin right here, right? So dbin. So you can see the distribution. This is the name of each. And then you can also get information from here as to what are their parameters themselves. Actually, I'm below where that needs to be. Yeah, blanking on it now. But base module. Nope, there it is. This is section 9.2. So page 43 is really where you're looking at in the R manual to get this guidance. And again, you've got a big table. But there we go. Okay, so here there's the continuous distributions. Where do we have y? Y is not continuous, so it won't show up under a continuous distribution. It's a discrete distribution. So here we will find it under, once we get past all of those, there we go, dbin right here. So this is telling us right now what needs to show up to make y become a binomial distribution. You need to give it two parameters, or two values, a p and an n. Right? So p being the probability, n being the number of trials. And in this case, you can actually the nice thing about it is you have the math of the distribution there. And why I say that's nice is because a lot of times, particularly if you've been working with code a lot, this is me like yesterday with class, and like you're getting towards the end and you're weary and you're bleary-eyed and whatever, and you're like, wait a minute, do I have the parameters right? This is a good place to go check. So just grab this syntax right here, grab this notation, compare it with what you think it should be in R, particularly when it comes to the prior distributions, because they're not always the same. Often they map on, but they're not always the same. So you want to make sure that they're identical. Questions?
Yeah. Fundamental question, kind of going back to last week.
Yes.
So in our particular case here, the likelihood function, that's found by iterating across possible values of theta and seeing for that value of theta what is the likelihood of that data, right?
Well, the function itself is given by the model.
Mm-hmm.
So you basically say, oh, in our case, this is a really simple example. Y is 7. We had 7 successes out of 10 trials. We'll just call it a binomial distribution. So that binomial distribution defines the likelihood function itself.
Right.
So does that help? So yeah, so it basically for any value of theta.
Right.
That's right. So yeah.
So like if I wanted to by hand graph the likelihood function.
Yes.
Sorry. Pick a value of theta.
That's right.
Find the likelihood of 7 out of 10 successes given that value of theta. Iterate the value of theta.
Yes. Pardon me for mistaking the question. The idea is that that's exactly. If you want to graph that likelihood function, you would have theta on the kind of the y, the horizontal axis, and then y would be, or the value of the likelihood would be on the top. And because we've observed n, which is 10 in our case, and we've observed y, which is 7, we can iterate, like you said, iterate across the values of theta to get that. Yes.
Like thinking forward to normal distributions, if we are assuming we know the variance, we would iterate across the mean
That's exactly it. That's exactly it. And actually, that's entirely the case. Hopefully we'll be able to see that this week, but maybe next week as well. We'll see. We'll start getting into that as well.
Sure.
But that's exactly it. So in general, the likelihood is expressed as a function of the parameters you don't know. So thank you for clarifying. My apologies for mistaking the question. I'll tell you what happened. I went to look for other questions and I found them.
Oh, sure.
And then I see Lisa Hoffman saying, "Hi, Daddy, love Huey." And so if Huey's listening, which I doubt he is, he's probably on Paw Patrol. We will actually we're playing. Let's see here. Other questions. Upload recent courses. Best wishes from Turkey. Thanks. Hi, Turkey. Katie says, so in writing this Jagz code, we aren't calling the objects in R. We have already. No, we're not calling the objects in R yet. The Jagz code is even though it's in R, it is not a function of R code itself. There's going to be a link, and that link is coming up in just a moment that I'm going to show you where it is. But we just need to keep track of what we're calling in the Jagz code itself, because we need to make sure that we supply the data that Jagz is expecting. Because if we don't, it'll happily, most of the time, happily just chug along, and what it's doing is just simulating data that have nothing to do with data, like our data, right? Does that help? Hopefully that helps. So let me continue on this, and I'll show you what I mean. Why here and why here right now are not yoked together, but to make Jagz work the way we need it to, we need to pass Jagz something that's called y. And so in the Jagz, once we have our syntax built, we go and pass it to Jagz to do the analysis through the Jagz model function. And in that Jagz model function, there's a place where data shows up, and that's where we pass to Jagz each of the things that we want the values to go to them. And I just so happen to call it y in my R code and call it y right here, but it actually has to be named y in a list for Jagz to know it. So it doesn't always have to be one-to-one with the R code. I just made it that way to be simple here. Hopefully that helps. It's one of those big picture not frustration, but it's one of the consequences of not having Jagz be directly embedded in R. Other questions or thoughts? See if anyone can hear that. Okay, the next step then, we said that y is binomial. So binomial had two parameters, a p, which we don't know, we're trying to actually estimate. So we're going to call that p what we call theta. That's been the theta in the example. And an n, which in our case is the number of trials. So there's j, which we're calling j is n for number of trials. So there's p and there's n. And again, that syntax form comes from this document right here, right? P and n for it. Now this document doesn't explicitly say p is a probability and n is an integer, but it's sort of implied. You have to sort of know the stat lingo to make it work. So that's another hurdle you have to get over. And if you have any questions, if you're using this on your own and you have any questions about these distributions, I'd be more than happy to try to help you. But right now we're just going to stick with binomial. So that's what we have. This is the likelihood of the data, the conditional distribution of the data. Right? But we know that theta needs to have a prior distribution. Right? So now we have to go and specify the prior, and that's where the prior shows up first. You can actually put prior below. You can put it in different order. I'm following the order that they had in the textbook for this example just to be consistent, so you have another reference to go to if you want to see it again. But you can put the prior below. And in here, we say theta. Now, theta is the thing we don't know. It's the unknown quantity. It's the parameter we're trying to estimate. So we have to give it a prior to make Bayes work. So we use the tilde character again that says theta follows, and we want to give it a beta distribution. So if you're figuring this out on your own, you say, okay, beta, is that a continuous or a discrete distribution? Continuous, right? It's for a continuous number between 0 and 1. So we go up the continuous distributions, we go all the way at the top, and we find, whoops, one more, beta. There's the beta distribution code. It has an A and a B. Those roughly map onto our alpha and beta that we saw before. And again, the way that we could have checked that is we could go and take a look at how what I called beta. In this case, I was pointing to the book. So what the distribution of the book said for beta. find out where A and B happen to be on that distribution and see that they're the same with alpha and beta. So then, with that, we end up saying d beta, and we have to specify the parameters of the prior. These are the hyperparameters. And we could change them. We can put them wherever we want, but for right now, we'll start the example with having them at 1 each, right? An alpha of 1 and a beta of 1. What that goes and gives us then is a uniform prior, right? The most uninformative prior you can have across the space of the probability parameter theta. Right? Any questions? So, in general, the form of the Jagz syntax starts with the model, right? In this case, the likelihood of the data, or the conditional distribution of the data given the parameters. And then for each of the parameters, the prior gets specified. Right? That's the key. That's at least the way I organize it in my head. Model first, then prior for each. Jahan.
Okay, so hyperparameter is always given, or
hyperparameters sometimes get estimated. It depends on the model. So for instance, in a multi-level model, in a CFA model, which we're going to get to in a few weeks, the parameters that we often think of as random, even when we're doing this in a traditional non-Bayesian framework, are the unobserved latent variables or the random effects, right? But those we say have a distribution. So in a CFA model, you say I've got, let's say 3 factors. Okay, what's the distribution of the factors? Well, it's multivariate normal. Now, what are the parameters of multivariate normal? A mean vector and a covariance matrix. Often we fix the mean vector to 0 for identification, and depending on how we identify the items, we also go and estimate some or all of the covariance matrix. In that case, one of the vectors of hyperparameters is fixed at 0, and one of the other set is actually estimated. So there are cases where you'll see that. For us, there's nothing to estimate these hyperparameters for because there's one observation and it just happens to be a probability. To estimate those, it's like having a one observation model, right? It's not going to go well. It'll probably let you do it. We could probably specify hyperparameter distributions and estimate them, but it's not going to be identified. Hope that answers the question. Other questions? Make sure we're good there. Okay. So now, once we have the text all in place, I'm just going to run some of these lines of code right here. There we go. In the way I've specified it here, the text object just shows up as a model01.text. It's just in R a character variable, right? So it's just literally just a string of text. The /n's that you see here are kind of next line characters. So that's where you get the spaces in it. But that's it. That's what our Jagz is going to read. So now, when we load the rjags package, to get this model and the data over to Jagz, we use the jags.model function. Jags.model, let's see if I can, there it is. Hey, it's right there. It's like I was looking this up before I was teaching this, right? But the help for it is a little bit helpful. It wants you to have a text file for the data. Jagz is traditionally run with, if you write all of your text in a separate file, it's just a plain text file, and then you point to it or read it in. But there's a way you can shortcut that in R where you don't actually have to output your text file and point to it. And that's by using something called text connection. There's a text connection function that turns your Model 01 text file into something that's passable to Jagz directly without having to, otherwise, without that there, you'd have to write your text file to disk and then tell it where on the disk it happens to be. It's a lot more direct. When we get to the R2Jagz version of this, which we'll just see shortly, that part of it won't have the text connection listed. But that's just a minor thing. So everybody, any questions? So the next part's probably the last hurdle of complication. We need to tell Jagz what our data are. And the way that Jagz or the R to Jagz package works is by you have to specify data in an R object that's the type of a list. Are you familiar with the? Let me. Even if you're familiar with lists, for those of you who might be, we have varying levels of R proficiency in class. The list object in R is a very general, generic term, right? So if you look at my environment in R, all these variables right here, each of these are of different types of classes. Each object has a version of a class, and you can actually see what type of object they are if you type the class statement. And if I put the term alpha in, it says it's numeric, which means it's just what's called an atomic vector. It's just a string of numbers that is expected to have the real number values, effectively. Floating point, I believe we'd call that. But YMAT and XMAT, on the other hand, you see them up in the data section of our code. Those are, you'll see that these are called data frames, or in this case, matrices. They're not data frames. So data frames and matrices are very, very similar. The difference between, so they're two-dimensional objects with rows and columns that you can index. The difference between data frame and matrix, and Brandon, or Dr. LeBeau, Professor LeBeau can probably correct me if I'm wrong on this. The data frames can have data of any type. So you have a character, you can have Boolean, you can have real numbers, whereas matrices are all of one type. They can either be all character or all numeric, and maybe even all binary.
Yeah, I think that sounds right.
Okay.
If you want to get really technical, data frames are technical lists.
Ah, there you go. So R, and this is the beautiful thing about R, and the frustrating thing, like it was frustrating for me for about 12 years, and then it became beautiful somewhere, right? Which was, it's so darn flexible that you end up getting into structures. Well, let's talk about a list, though. A list is a way of combining a bunch of objects into one big named thing, right? So let's imagine I wanted to say create just one container for anything I want to put together. Let's just call this my list. So I'll create a variable named my list, and I'll call this the list. I'll use the list function to do this. So the list function then now takes whatever I give it and puts it into my list variable. And let's just say we want to do the crazy thing. I want something to contain a matrix and a numeric just value, right? So we could say matrix equals, let's call it XMAT, since we used that before, and number equals alpha, right? So what have I done here? XMAT is the matrix that I have up here in my environment already. So it's going to show up under my list with the name matrix. And then number is going to have a name, and it's just going to have alpha. So if I hit enter. By the way, my R code, I love seeing people squirm because I really hate the assignment character in R. If that's that's like the most common thing you use in any computer science package is assignment, and you have to type more than one keystroke to get that. It's inefficient. Now, I'm guessing you probably love it, right, Dr. LeBeau?
I just like it because it differentiates the argument, the difference between assigning versus specifying an argument. That's my only reason why I use it.
I hear you. I think like history of it, didn't this come from Lisp? I want to say the Lisp package, and at the time they had there was a machine, I want to say I read the story somewhere, there was a machine that actually had an arrow key. So it was a one-press assignment character. So I will say it's very flexible. Sometimes you have to use it if you're doing non-standard assignment or non-standard evaluation. And if you want to go left to right assignment, you could do that. But then again, and if you think of like every other package of software or coding, how many of them allow you to do that left to right or without having some type of really good catch? So I rarely have left to right assignments. I want one button. That's it. And actually, back in the early days of R, I want to say they didn't allow the equal sign back in like 2001, right? Thank you. And so that made me so angry that I just quit it because they would allow you to have like an underscore to be the assignment, but it was ridiculous. So anyway, sorry. Once I saw that R allowed equals, I was like, all right, okay, at least we can be friends.
We're back in.
Yeah, that's right. Now there are cool things you can do with it, right? You can say one. You can assign like this, right? You can assign left to right, or but you can also do the other thing, which x equals y equals 2. Like you can multiply assign in a single line with equals anyway. So blah, blah, blah. Anyway, what does my list look like? My list now is an object. It is a list. But if you want to go and take a look at it, lists have lengths to them. So you use the length function. It should be of length 2, which is what other... I can't spell it. So there's length of list. The length of it's 2. That means my list contains 2 things. And those 2 things you can access like you would variables in a data frame. You can say my list and then put a $sign, and it will ask you, do you want the matrix or the number, and then you can get access to it. So the same thing goes to pass data over into Jagz. You have to create a list. The data has to be named what you want, what you expect those values to be in Jagz itself. So in this case, we know J, we know Y, we know alpha, and we know beta. So our list has to have a J, a Y, an alpha, and a beta on the left-hand side of equals, naming each of those terms as we pass it over. Any questions?
So just to be clear,
Yeah.
the left side is coming from the text for your Jagz code, and the right side equal sign is from your earlier R script, right?
So that's right. That's exactly right. And
So
then the
that-
list
in the
function.
case that, in this case, your R code script was the same thing you used in your Jagz.
That's exactly it. That's exactly it. I named them all. I tend to name things the same if I want just to keep it straight, but it may be the case that the left side and the right side don't match for you. But yes, every term in the list function. Thank you again for adding that. The left-hand side is showing up in Jagz. Those are terms that Jagz is expecting effectively, and the right-hand side is the terms that are from R. So the terms that you've given to it. Let's see if there's any other questions. Okay, other questions. Okay, so the next thing, we can tell Jagz how we want to initialize our parameters that we don't know. So in this case, we can put theta equals, and this is a random uniform, the value from a random uniform variable, again in a list. I will tell you that as we go on, we don't actually have to specify the inits in many ways. And actually in the Jagz.model, is it required?
It says it'll pick up if you don't assign.
That's right. That's right. So it's not actually required, so we can thankfully get away with it. Why I say thankfully is because when we get to a factor analysis, right, not only are we looking at the item parameters, the loadings and the unique variances, we also have all the latent variables we have to specify too. So at some point you start specifying thousands of things, starting values. So the other part where this might come in handy, however, though, in initialization is if you run a Markov chain and it hasn't converged yet and you want to kind of pick up where you just left off, the starting values you can supply are the last values in the chain that you previously ran. So that is helpful, but generally it's easier to pass those over because they're contained in some other object, some other list in R itself. Okay. Now, I haven't even talked about how MCMC works. We're going to start getting into that as we go forward. But actually, I said the first day of class, MCMC, every parameter has a value at every iteration of the chain. And a full iteration allows every parameter the chance to change its value. Right? So it's going to take this random walk, and we're thinking we're sampling directly from the posterior distribution. So eventually it gets into the posterior and it jumps around. Inits would be the first value that you give it to start. Right? And in some contexts, those are really helpful, and in some contexts, they're not. So, and it takes some experience to figure out where that is.
Good selection could make it converge faster. Right?
It could.
And poor selection could make it converge very, very slowly.
It could. However, I will say that the Jagz, the way it samples values, it tends to be pretty efficient because it figures out which method to use.
Sure.
So it's going to use effectively Gibbs sampling here,
Right.
which even if we make bad selection, we typically recover in 1 to 2 steps anyway.
Yeah, it'd be worse in like Metropolis or.
That's right. And if you're doing rejection sampling, what it depends on is how big of a variance of your proposed values happens. So if you tend to have a small variance of proposed values and you're really far off from where the posterior is, you may never recover within the length of the chain. In theory, you can run it long enough, it will recover, but in complicated models, that takes a really long time. So I would say that if you're building your own, and then people might laugh about building their own algorithm, but that's actually something that you're not far away from here. It's not hard to build a Metropolis algorithm. Gibbs is a little more complicated because it involves the math, but if you don't want to do the math, the Metropolis will work pretty well. If you're building your own, that's something to be considering. But generally speaking, when you're using Jagz or Stan, you're in good shape with what it's going to pick for you. So next. Now, a Markov chain is kind of one length of this random walk where you start with a starting value and you're kind of jumping through iterations, allowing that value to jump. You can run multiple chains for the analysis. And typically it's done where you have multiple chains where the starting value is randomly changed, right? So each starting value changes. Why we do multiple chains often is because we want to see that our posterior distribution converges to the same area, right? So when we lay the multiple chains on top of each other, we shouldn't see one chain that has a kind of a caterpillar plot up here and another one that's a little bit lower. We should see them right on top of each other. Now, generally, this is one of those things where for choices of conjugate prior, at least in this case, we're in what's called an exponential family of distributions when we have a beta distribution. And an exponential family of distributions is convex. It's right. That's the downshape. Convex and single peaked when expressed at the likelihood function, right? So when expressed in the parameter. So there is no other place for this to converge to. Is what I'm going with, right? Where we get to places where you say, well, I'm not going to necessarily call it beta as a prior. I might put some other weird prior on, like a mixture prior or something like that. Then we might end up in a place that has multiple peaks. And in that case, that's where the multiple chains really come in handy. Here, we expect these chains to lie right on top of each other. So, finally, adaptations. Adaptations are... in this case, probably not necessary because the algorithm that Jagz is going to use, which, by the way, you're not specifying. You have to kind of go out of your way to tell Jagz which way to sample. We haven't gotten to algorithms yet. That should be 2 weeks from now. But the algorithm it's going to use doesn't need adaptation. There's nothing to adapt. It's a Gibbs sampling algorithm. So, but later on, when you're not doing that, when you're doing a rejection sampling like a Metropolis algorithm, Metropolis Hastings, there's a period that happens before the burn-in. Right? So remember, in chain we have generally starting value. We have a series of values that we discard called burn-in because that's sort of letting it get towards the middle of the posterior. And then we look at the last series as our posterior distribution sample. Adaptation happens before burn-in. Like it takes the random start, runs the algorithm a little bit, and at various intervals of that adaptation phase, it looks at how efficient it is at choosing or switching values, right? The thought being that if it's switching values every step, then kind of where you're sampling from has too small of a variance. It's hardly changing the parameter, so it needs to get a little bigger to be able to sample the space more. Or on the flip of that, if it's hardly ever changing, if it takes 10 steps before it changes, the variance is too wide, it needs to come down a little bit. It's usually what happens. There's other ways of adapting as well. But in that adaptation period, what it's doing is trying to hone the algorithm so it's more efficient when you get to burn-in and posterior. So I like adaptation. One of the reasons I'm afraid of using the next package is because yesterday I was reading somewhere and it said adaptation turned off, and I'm like, it shouldn't be, I don't think, but it could have been for another reason, so I had to do a little more investigating. Any questions?
So it's adaptation, burn-in,
and then sample. That's right, yeah. Adaptation and burn-in are not even, adaptation isn't even recorded. Sometimes we record the burn-in, but generally speaking, we don't do anything with it. But sample is where we take those values and then we use them to calculate our distribution. Thanks.
How did you decide
That is a tough one to understand. There is no good knowledge a priori about it. Generally, when you do a model, as you start working with a certain class of models, you'll start to know a little bit about how quickly they converge, particularly with data or when real or simulated. This is the default. The default here is 1,000 is what I put on there, just to do it. That also doesn't make any sense either. There are other algorithms out there who try to help you with it. So in SAS, Proc MCMC has takes that adaptation period and breaks it into chunks. So basically it says, I'm going to have these little windows. I'm going to let the algorithm run. At the end of that window, I'm going to see if I need to change the specifications. And it will have a sort of a target of acceptance rate. You want to have like I think they have 47.5% of the proposals are accepted because Andrew Gelman said it once or something like that. Anyway, they have a reference to Gelman. And actually, Gelman is brilliant when it comes to science, but a lot of people just say, well, Gelman said it, then I'm good, right? That's how brilliant he is. I think I get snarky when I think of blind allegiance to everybody. And I think Gelman would even say, well, he's capable of making mistakes as well, right? We all are. But that being said, it's pretty good. SAS does it, these little chunks of adaptation until all the parameters fall in line under that window. So you don't have to choose how long it goes. What you can do is stop the chunks. You can say, all right, if everything hasn't been fixed by 24 of these things, just run the whole thing, right? So, and generally speaking, it, for most models I've worked with, gets done within 10 to 12 or so. So it's tough to tell. Jagz, the way you make it work, if you don't like how long it works, if you run this analysis and you see the chain is just not moving very quickly, if it's very slow, a lot of high autocorrelation, you can go back to this portion and readapt, or there's another function called the adapt function. It will just take model 01 that we created and run a longer adaptation period for it. That answer your question, hopefully. Yeah, how do you know what to do with any of these? There is no good answer, including number of chains. Right. So hopefully we'll see this a little bit better as we go a little bit further. So now I'm going to run this example right here. Could not find function. That's because these chunks right here hadn't been run. I ran them, but then I ran something else. So now when I run this, it'll show me this as output right here. Compiling model graph, resolving undeclared variables, allocating nodes. That is it telling you kind of the picture of how it's working. It's a directed acyclic graph. The nodes are the parameters it's trying to estimate. The observed, this is your data. It has one observed stochastic node. That is this thing right here. That's y. Because you gave it y, it's like, oh, I observed it. I have data for y. I'm going to use that as my likelihood function. It has one unobserved stochastic node. That is theta right here. But the good news is that if you look at that, if you count 1 plus 1 is 2. God, this is grad school. I shouldn't have to say. Anyway, theta and y are there's two terms you see that are on the left-hand side of the tilde. And that's what it's saying. These are nodes. When you put something on the left-hand side, it's a circle in this graph. I don't want to get into circles or squares, and I actually don't want to get into the graph. I just want to make you think. These are the random terms that are there. Some we have data for and some we don't. So it did that, and then it initiates the model, and that's the adaptation. It runs this lightning quick when we only have 2. It's very, very fast. Now, I'm sitting here thinking, you don't have to do this. What did it do? What's it using to actually do its work? There's a list samplers method or function where you can say, tell me what samplers Jagz is using to make this work. There's some 13 or 14 samplers it has. They're all of different varieties of algorithm. The bugs binome slicer is what it's using, which is effectively, from what I understand, of it, as I try to get into it a little bit more, is Gibbs sampling. Right? This is a conjugate prior binomial distribution that knows how to make it work fast. So that right there, even though it looked like when we ran this section of syntax, it initialized the model to 100%, we haven't sampled anything yet. What it's done is it adapted. But we don't have anything that we're going to go and draw for a posterior. To get the work done, we need to use another function called Coda.samples. This is where we passed to Coda.samples our model object. That's the one that we just created and adapted. We tell it the variable names that we want to track in the algorithm. In this case, there's only one that we're really concerned with. It's theta. And we can tell it the number of iterations as well. And Coda.samples has other places where you can put the number of thinning intervals, which basically is how many iterations do you want to skip to move forward. So we run this now, and that has another display of progress bar that shows we got to 100%. So we're done. The algorithm ran. Now the question is, did it converge? Did it work? What happened? And this is where I get ahead of myself. We really should look at what comes back. So Model01.samples contains, it's a list that contains a whole bunch of values from Jagz that came back from the Jagz program. Some of that includes the model itself. Oh, anyway, maybe not. But what we can do with it, and I should start here, is plot. We can plot the chain first and take a look at what we have. So let's take a look at this. This is our trace plot of theta. This is the number of iterations, right, between 1,000 and 2,000. It cuts 1,000 off for the burn-in. And what we want to see, all 5 of our chains are placed right on top of each other. The trend lines for all 5 are given by that thin line there. And if it's really hard to see all 5 of them, that means that's a good thing. They're all kind of in the same spot of this posterior distribution. That's what we want for it. So this is the trend, kind of the trace plot of theta. This is sort of the trend across the iterations of the algorithm. That's the first place we go to assess convergence is to look at it. Then we have a bunch of other statistics we can use to actually determine whether it's converged. But looking at it is like the first way of thinking of it. So again, that trace plot is telling you the value of theta, the value of this probability at every step, every iteration of each chain. That's what it's telling us. So then, we have 5 chains. We have 1,000 values each. It then goes and says, all right, you know what I'm going to do? I'm going to grab these 5, forget which chain, I'm going to erase the value of the chain. I'm just going to pool them together and look at that set of data and then try to smooth a density function out of it. See what a density might look like. And this right here, this graph on the right, is the density. It's our posterior distribution of theta from this analysis. So in the previous lecture, when I was saying, oh, we know what the posterior is, now we have to summarize it, this effectively takes that place, right? So we say, oh, yeah, we would, with this simple model, we probably would never do MCMC with it, but it's a nice way of kind of getting a start with MCMC. This is the story. This is all we have about theta. This tells us everything about it that we want to know, right? Yeah.
Will the algorithm still try to pool things if there is sufficient evidence that the chains are pretty different?
Yes. And that's where
we have to be on the lookout for that.
Absolutely. And that's where you'll start to see the multimodal distributions here. As it is, this thing is not nice and symmetric. I mean, it's symmetric, but you'll see little hiccups to it. And that's just because part of it's sampling error, right? You're talking about trying to smooth in a density function at all parts of the parameter space, right? Well, we sampled it 2,000 times, which is a lot. But if you think we're smoothing it in, we're trying to get it to be sketched perfectly, we may need to sample even more to let it go over that, pass over that more if we want it to be smooth and symmetric. That's right. It's right. Yeah, and if you think about how long, if we run this, we allow this to go, 100,000 to infinity, we should have the right posterior. We should have a picture of it. But it's tough. Yet again, an asymptotic thing, right? Always rely on large samples. But there we go. Other thoughts or questions about this? Okay, look over here. Nope. So how do we summarize it? Well, let's just, there's another way that we can talk about values, or how do we go and say whether they converge. There's a whole bunch of output diagnostics, they're called, statistics that basically run. One of them is the Gelman and Rubin convergence criterion. It effectively pools the within chain variance and compares that with between chain variance, and it weights it by certain values. But basically, you want this value to be 1. If it's 1 is perfect, it means it absolutely is converged. Generally speaking, people have rules of thumb. You want it to be less than 1.1 or 1.2. The closer to 1 it is, the better it is, the more converged it is. And so what this is telling us for our parameter is that the point estimate of this statistic is 1. And if we were to go form a confidence interval around this statistics, the upper value of it would also be 1. Right? This is converged. This is really, really converged. But we could see that with our graph. The hard part with plotting is that when you get a model that has, again, if you're thinking of factor analysis, you've got 1,000 people in a data set, you've got at least 1,000 latent variables, if not 1,000 times the number of latent variables you have each. You're not going to be able to look at all of those. Right? You need something to go and summarize how many of them have converged and how that works. But if you look at your analysis and this were to not have converged, if Gelman's statistic would have been, it's like 1.3, without convergence, it's not good to look at the posterior distribution because you're not sure you're in the posterior distribution, or you didn't sure you have a full picture of that posterior distribution. So want to check for convergence before you look at anything else. I know that I put the summary statement before I put these two values, which was bad. But the summary statement then tells us, okay, what are our point estimates? This now, once we've figured out, so what we've done, we've built the model, we've run the analysis, we've run the Markov chain, we just assessed convergence and it converged. So now we can talk about the results. And what are the results? Well, we have to summarize that posterior distribution. We have to summarize that thing. How do we summarize it? We summarize it. The summary statement starts to give us some of that information. The mean of that posterior distribution is 0.6669. And if I go down in my plots down here, we saw that when we did the actual theoretical version with the alpha beta of 1,1, a uniform prior, we knew that the mean, which is an EAP estimate, which we called last time EAP, is 0.67, which is approximately where we are right here. We can see that the mean is approximately the same. That's one way of summarizing it. You'll note in the previous lecture I made a point of saying the MAP, the mode. There is no mode that comes out with statistics here. In fact, if you think about it, how would you find the mode? You'd have to find the peak part of the density and then map it over the parameter. You could do that. There are functions that will do that. There are packages that will do that in R, but it's just not one of the statistics that comes out. And that will cause a problem for us as we go a little bit more forward, particularly when we get into linear models or when you talk about variances. Because that's one of the bigger differences between frequentists and Bayesian work. So the mean is 0.666. That's the mean of the posterior distribution. The standard deviation of the posterior distribution is 0.129. Those are two summaries that often show up in reports. They have versions of the standard error of the mean as well, based on whether or not there's some autocorrelation in the chain. I didn't go and calculate the correlation, or whether or not you have or ignore it or versus not. But those are other ways you summarize it. And finally, it gives you the quantiles for each variable. This, you could look at the value of the parameter between 2.5% and 97.5%. This forms what we call the credible interval. Right? It's not the HPD, not the highest posterior density, which is a credible interval with the smallest interval, but it is it is a summary statistic we often see. This is basically saying somewhere between 0.39 and 0.88 lies kind of the middle 95% of the chain. Does that help? So that last part there, that shows up every time in MCMC. We're always doing that same stuff. Run the chain, assess convergence. If it's converged, start to describe results. This is a really simple example. There's nothing we can do here to go and say the analog of a hypothesis test or significance or things like that, even though we don't want to do that in Bayes. That's not what we say. We just more look at that. Questions? Okay, so I'm going to go simplify this in some respects. I'm going to use the same model and we're going to run it in the R2 Jagz package. The main difference between R2 Jagz and Jagz is that instead of enclosing your text of the model in quotes with a model and brace and then end brace in it, here you can enclose it in R function, right? So we're basically saying our model is equal to, becomes a function in R. We don't have, in the text file up here, we don't have the model and open brace or close brace in it. We just have the text of the function itself. It's the same part that's in the middle there. We still have our data. We could still create initial values. This time the initial values get created by a function as well. But to pass the data to Jagz now, we use what's called the Jagz function. The Jagz function then has a spot for data. It's the same list that we did prior to this. Inits, initial values, parameters to save. The model file is the name of the function. You can specify the working directory. I don't think it's actually going to output anything, but if you had model files that are in the working directory, you could tell what that is as well. But this right here, instead of having to run Jagz twice to do adaptation and actual sampling, this will do it all at once. Oops. And of course, I actually have to load it up first. There it goes. So now you'll see all of that works. One little other piece of information I didn't show before is the module GLM loaded. Module GLM loaded, this thing, I just highlight it here. That, by default, well, let me back up. Jagz has a series of modules that are supposed to make certain analyses go faster. GLM is generalized linear models. You can tell Jagz in syntax to load the module, but by default, the R2 Jagz package tells it that already. Even if it's not necessarily going to use it, it loads it. So it makes it a little bit easier. All of this other part is the same that you saw before. Then you see initializing model, and the first sequence, that's adaptation right there. So it is adapting, actually. And then this part right here is sampling. Right? So you see those two 100%. That means it compiled the model, adapted it, the algorithm, and then sampled from it. And then, but from that now, there's a little bit different ways that we go and plot things. We can do the trace plot function gives us the plot, or at least it should. I've been having this issue. You know, I don't have time to wait. How about we just do this, actually? Yeah. I'm having this issue yesterday, and I don't know what I've done, but somehow in working with this, I'm going to get RStudio hanging on places where I didn't expect it to. And so I'm not sure if there's a connection open that shouldn't be or whatnot, but now I've got an issue because it's the spinning wheel of death here. Let me see if I ran this whole thing. Did I? I did. Okay, so I think you can see all of this. I'm going to switch over to my Markdown output here. But now under the result of this trace plot function is going to show up over here. This is me running it previously. Here you've got the deviance. Deviance is a statistic that we're going to get into in just a little bit. When I hear the word deviance, I think of somebody who's like evil. But you know, like a latent variable we're trying to measure about evil. Now that's a scale ACT should invest in.
Yeah, That's moving.
Got a couple of those I've been thinking of, you know. Then we also get the trace plot of our parameter. Again, this doesn't put the trend lines for each of the chains, but it has all 5 chains listed on top of each other. This is the comparison of the trace plot function with just the plot function right here. It's basically the same. And we get our summary and we get our value of this. Again, deviance is something we're going to get into a little bit later. It's kind of like a likelihood statistic, but we'll get into that several weeks here. There's so many things to keep track of at the beginning. It's hard to kind of keep them separate, but it's going to show up a lot as well. Finally, one of the nice things about Jagz, or the R2 Jagz package, is it actually comes with a function called auto Jagz. That sounds nice, right? What does it do? It runs the chain. It assesses convergence based on some criteria you can give it, or its default criteria. And then it says, hey, if it hasn't converged, I'm going to run it longer. So it goes back and reruns the chain for you.
That's nice.
And it keeps doing this process. It's very nice. Have any of you used M+ for Bayesian at all? So M+, the way it works, also sort of auto checks for convergence. It sort of takes that out of the user hand. But one of the nice things about this is if you specify your model object and you don't really give it a whole lot of iterations or whatever, you can just go and run it in auto Jagz and it will just run it to completion for you. The bad news about that is, you click run on this and I don't know, what's the longest time you've ever had one single analysis run before? Anybody had it run a day before? No. Yes? How about a week? How about 3 weeks? I think I've had a 6-week analysis before, right? All right, so if you have a 6-week analysis from auto Jagz, oftentimes there's something else going on wrong there. So you sort of have a blessing and a curse with it. For most of the models you're going to see in this class, it shouldn't take very long to run them. By that I mean minutes to hours, right? This one just took seconds.
If you go to console and push enter, the graphic will show up.
Oh, that's where it is. Thank you. See, I've got learned helplessness now. It's like everything is like breaking around me, I feel like, or I'm just having these shocks to my system. And it's like, oh, I've done something wrong. I'm not even going to fight with it. Because usually when I fight with it, you get this like raging maniac behind the computer. I don't want to let that guy out in front of class. Yeah, I'm like, oh. Lisa knows him. He's best just left somewhere else, right? Anyway, thank you, Aria.
There's entire YouTube montages devoted to the raging guy behind the computer.
Oh man, I run out of patience with devices. I'm like, you work for me, you know? But no, it's like the one place I could be like, hey, you work for me. Anyway, I should be nicer, right, Siri? Any questions about this? Any thoughts? Anything before we go on? All right, let's take a break. I'm going to stop the session right now. Stop the stream. We'll come back in about 10 minutes. I'll have a brand new stream going, and we'll go from there.